Okay, we've already kind of started this unit with our s'mores lab, okay? So stoichiometry is our next unit, and we're going to use the concept of balancing equations, the mole, and be able to relate the reactant side of the equation to the product side of the equation, okay? Now, stoichiometry is kind of a scary word, and I think it's kind of funny that nobody really explains what the word means more times than not to make it less scary. But it's actually a Greek stemming word coming from stoiki, so let me write it, stoichion, which means element, and metron, which means measure. Okay, so all stoichiometry actually means is the measure of elements. Okay, so we're just relating how much of something of the elements that I have within a chemical reaction. Okay. So we use everyday chemical equations, and this is just like recipes, just like we did with our s'more lab, okay? A balanced chemical equation provides the same kind of quantitative information that a recipe does, like when you make a s'more, okay? Ingredients are like reactants, and then your cookies are the products. Or like in our s'more activity, we had graham crackers, marshmallows, and chocolate making one s'more, okay? So let's just kind of break that down just a little bit further to give us another example of what we did with our s'mores, okay? Chemists use balanced chemical equations as a basis to calculate how much reactant is needed in order to produce a product, okay? So let's just look at this. So if I want to make brownies, okay, I need brownie mix, 1.5 cups of water, 0.5 cups of oil, 3 eggs, and ultimately I'm going to make 16 brownies, okay? How much of each ingredient would I need if I wanted to make 32 brownies for one class, okay? Hopefully you realize that 32 divided by 16 is 2. So all of these ingredients would have to be multiplied by 2. So for example, I would need 2 brownie mixes. I would need 3 cups of water, right? I would need 1 cup oil, and I would need 6 eggs, okay? And then ultimately you could do the same thing for your 64 brownies, realizing that this is 4 times, meaning you would have to multiply all of these by 4s to make 64 brownies. Now this is something that you've probably done before, okay? So let's actually look at how we can use now, moving from brownies to a chemical equation, to kind of think of the same concept, okay? So what does a balanced chemical equation actually tell me? Can tell me the number of atoms, okay, the number of molecules, moles, mass, or volume. So ultimately, I can find all 5 of these things just from a chemical reaction, right? So for example, I don't have any atoms in here, but I can use these coefficients, so 1, 3, and 2, all represent the number of moles based off of this balanced chemical equation. So for example, I have 1 mole of N2, 3 moles of H2, and 2 moles of NH3, okay? And once I get moles, you know that you can convert to molecules, atoms if we had any. We don't have any atoms in here, but you can ultimately convert to it, mass, and the volume. Okay, I'm not going to walk through that step by step because I feel like we've been doing that in class pretty readily, but we'll do some more examples when we talk about what does that actually look like based off of a chemical equation. Okay, all right, so the next page, let's look at mass and chemical reactions. Oh, I lost my screen. Okay, sorry, before my screen cut out, I just want to talk about this for a second. We're going to skip this for now. We're going to go, I feel like we've done this with the mole, our s'more, so I want to skip that and actually start looking at mole ratios and what they are, okay? We will be factor labeling, so if we can refresh our memories, factor labeling is saying question mark, the what, so like what am I looking for, equals the given, and then you set up a conversion, okay? And if you need multiple conversions, you can keep going. So that's what factor labeling is, okay? So we're going to use the same thing in this unit. So if you like the mole unit, you're going to love stoichiometry, okay? So a mole ratio is just another definition of a conversion. So if you remember from the mole unit, we had multiple defined definitions for conversions. For example, if I say how many atoms are inside of 1 mole, hopefully you would say 6.02 times 10 to the 23rd. Hopefully you would say the same thing if I say how many molecules are in 1 mole. Hopefully you say 6.02 times 10 to the 23rd. If I say how many grams of something are inside of 1 mole, you say, well, what am I talking about? Because I have to look at the periodic table to figure that out. And then lastly, you know that you have to find, if I have 1 mole of gases, that I have 22.4 liters available of that gas, okay? A mole ratio is just going to be another defined conversion that we're going to use that equals 1, okay? And we use the chemical reaction, and this is why it's so important that you know how to write chemical reactions. We use the chemical reaction to develop the mole ratio, okay? So let's look. If I have copper and silver nitrate making copper nitrate, copper 2 nitrate, and silver, I can relate their mole ratios to how much of something is being made, okay? So for example, if I'm starting with 1 mole, because there's a 1 coefficient in front of the copper, ultimately I can make 1 mole of copper nitrate. And that makes sense, right? Because there's 1 copper here and 1 copper inside of copper 2 nitrate, okay? If I start with 2 silver nitrates, I ultimately can create 2 silvers, okay? That is what these numbers out front from a balanced chemical equation tell us, okay? And we call them mole ratios. So if I wanted to develop some mole ratios from this balanced chemical equation, I can. What I can say is, I can say for every 1 mole of copper, I will make 1 mole of copper 2 nitrate. Look at that. I just made a conversion, okay? These two are related to each other based off of the chemical reaction. I can do the same thing with copper and silver. For every 1 mole of copper, I can create 2 moles of silver based off of this chemical reaction, okay? I could keep going here, and these reactions could be flipped if I'm moving from the product to the reactant side. I think it's important to note here, we're moving away from just having 1 in relationship to a mole. We can now have more numbers than just 1, depending on the coefficients from the balanced chemical equation, okay? So let's look at an example from this. So this question says, calculate the number of moles of silver produced when 2 moles of copper are used, okay? Using factor labeling, I say question mark, what am I looking for? So my question mark is moles of silver, and that's equal to, what am I given? I'm given 2 moles of copper, okay? And then I'm setting up a conversion. What unit needs to be canceled? Moles of copper. What unit do I want? Moles of silver. And luckily, I now have a relationship between 2 moles of something because of balanced chemical equations. So I'm going to look up here and say 1 goes with copper and 2 goes with silver. And then I can say, oop, not the 1. I can say moles of copper cancels. I'm left with moles of silver. I can plug it into my calculator. 2.0 times 2 is 4. And then I need to keep that sig fig, so it's going to be 4.0 moles of silver. Okay? Just like when you're making a cookie or something. Okay? So based off of this, now that I have number of moles, you can ultimately convert to anything. You can convert to grams, you can convert to atoms, you can convert to liters if it was gas, okay? And we'll talk more about that in an upcoming lecture. But first, I want you guys to practice writing chemical reactions, balancing them, and then finding mole-to-mole ratios. Thanks, guys.